Hi, I'm Mohit Yadav and I teach at Scalar Academy. After taking more than 200 interviews, I've come to a realization that most people lack one common trait, which is to design a good relational database. Now, why this problem arises? The root cause of this problem can be attributed to that many people come from a NoSQL background and hence they try to denormalize everything and put all the attributes in a single entity. Therefore, it becomes very critical to understand the basic fundamentals of schema design. This will not only help you in clearing the interviews, but it will also help you in building a repo and having technical discussion amongst your peer group. If you are someone who often finds it difficult to convert the real world requirements into the entity and relationship diagrams, then this video is for you. In this video, we are going to discuss about relational schema design using LinkedIn as an example. We are going to discuss about one-to-many relationship, many-to-many relationship. Apart from that, we'll also see when it makes sense to separate two entities even though the columns in both the entities are same. After this video, you'll be able to convert high-level requirements into relational database schema with ease. Now, to design any relational data store schema, all you need to do is list down all the features. Then where you need to identify all the entities and relationship that will support your feature list. To do that, underline all the nouns and verbs. All the nouns will then correspond to either entities or it will be an attribute in one of the entities that you have already listed. The verbs will translate into either the status changes or the relationship between two entities. Now let's see this trick in action and design schema for LinkedIn. So let's go ahead and see how to apply those tricks in action. The first feature is that user should be able to view and edit his profile, which contains the following information. This gives us a hint that there should be a user entity table. So let's add user entity. It can be a user profile as well. Let's keep it user profile for now. Every entity that you create will have one attribute, which is ID. This will basically be used to uniquely identify a user profile. The other attributes would be coming from the next set of requirements. On top left, a user should have profile photo. On the right side of profile pic, we should also show name and contact information. So let's add these attributes inside a user profile entity. So we'll have a profile pic. Profile pic can be stored in two places. One is in the database itself. If you store the profile pic in the database, the amount of storage that is required to store all the information of the users will be very large. So it's wise to store all the images and video links that are associated with a particular profile into a file store like S3, or we can also store them in a CDN. Right? So instead of storing the profile pic, I'll store the URI, which will either correspond to S3 or CDN or maybe any other file store as well. The next information that I would have to store is the name and contact information in form of an email or phone number or both. A user can have multiple skills. So there are two options of adding the skills. The first option is add that as a list object in the same user profile table. So if I am adding this in the form of a list, how that will come up is sample values will be Java, JavaScript, and so on. Right? This poses one major problem. The major problem is that if I want to find out all the users who have Java in their skills mentioned, so the problem would be that I would have to write something like a select star from user profile where skills like Java star, which means that this is going to be a scan operation. So if I have multiple rows in my database, then I will end up scanning all the rows. If I have 1 billion rows, I will scan 1 billion rows. So this approach will not scale. The other downside of this particular approach is that I will not be able to auto suggest skills to the user, because that will be again a scan on all the rows that are present in the database. So what we'll do is we'll add one more entity called skills. Now this skill, there are two ways of adding skill, right? Either we can have the skill ID, name and user ID stored directly here. If I do something like this, then again, autocomplete will be slow because there will be multiple users and multiple users will be having multiple skills. If you look closely, the two entities, the user profile entity and the skill entity, what is the kind of relationship between these two entities, right? So user can have multiple skills. Similarly, a skill can be having multiple users, right? So it's a many to many kind of a relationship. To model a many to many kind of a relationship, what you should do is you should create a mapping table called user skills. This will, again, all our entities have an ID, so it will start with an ID. We'll also have a user ID here and skill ID. And we can remove the user ID that was there in the skills object. If we read the next set of requirements, it states that we need to keep information about educational institutions and employers. And if you look closely, the attributes over here in the educational institutions and the employers are same. So what I can have is I can create an entity called organization. Inside an organization, I can have an ID field and all the other fields that are there, depicting name, start year, end year, and let's say description. And I will need to have one more type. This type will store information of institution or company. So from the looks of it, or for the given set of features, this table works really well. The challenge over here is that what if I want to add other attributes? Let's say I want to add CGPA in the educational institution and I want to add salary details inside employers. The problem here that comes is that I will have to add CGPA as a one column here and salary also as one more column. Now depending upon whether the type is institution or company, either CGPA will be null or salary will be null. Now it is not a very good idea to enforce application logic in your database. Just by looking at the database, you should be able to figure out that what are the what each column means. So to avoid such kind of a problem and to have a design that is extensible, what we can do is we can split this into two tables. One would be a education and the other one would be a company. Both will have ID, both will have name, it will have start year and it will also have end year. Type is not required because we have already split the table. But this alone will not be able to give me any sense of which user went to this particular university, which users went to this particular company. Now, what is the relationship between user and education and user and company? We would realize that a user can go to multiple companies and he can also go to multiple institutions for completing his education. Similarly, an institution might have multiple students who are studying in it. In a company also there can be many employees. So it's again a many to many kind of a relationship, and we have learned in the example above that whenever we have multiple many to many kind of a relationship, we create mapping entities. So there will be one table for user education and one table for user company. The attributes will be ID, user ID and education ID. Education might not be a better word, or the better word can be institution over here. So we'll have ID, we'll have user ID and we'll have company ID as well. Now if I want to find out all the users who have went to a particular institution, what I'll do is I'll go to user education table and I'll query select start from user education where education ID equal to the institute ID. The next requirement is to have recommendations. Now a particular user can either give recommendations or receive recommendations. Since this is a list, it does not make sense to add this in the attributes of your particular user. It makes sense to have a separate entity. So let's go ahead and create a recommendation entity. We'll have an ID, the person who is given the recommendation, so let's say user ID for that, and it will also have a recipient ID, right? Do I need to create a mapping table in this case? Now a particular recommendation will have just one user ID and it will also have one recipient. That information is actually captured in this particular table, so we don't need a mapping table in case of a recommendation. So if I want to find out all the recommendations that I have, what I'll do is I'll go to recommendation table and I'll select star from recommendations where recipient ID equal to my user ID. So the next requirement is having connections and followers. How connection and follower work is that if A sends a request to B, that means that A will be able to see all the public posts that are made by B. If B accepts that particular connection request, then B will also see all the posts that are made by A. Let's have a design that can model this particular feature set. So we'll have a connection table. Inside this connection table, I'll have an ID, I'll have user 1, user ID 1, and I'll have user ID 2. Whenever a new connection comes in, I'll add that particular row here. And as soon as B accepts the request of A, I'll add one more row. So if I want to find out anybody's followers, all I need to do is select star from connection table where user ID 2 is equal to the given user. So for example, A sent a request to B. So A is a follower of B. So if I want to find out B's follower, I'll need to query the second column, user ID 2. And as soon as it's a bidirectional mapping, I'm adding that particular row as well. So I'll be able to find that out as well. The problem, however, is that I'm taking 2 times the space that I should be taking. So to optimize on space, what I can do is have one Boolean column called is accepted. Now if A and B are a connection, not a follower, that means that A sent a request to B and B accepted that particular request, I can keep the accepted flag as true, otherwise it will be false. Now if I want to find out all the followers of A, if accepted flag is true, then I'll query based on either user ID 1 should be equal to A or user ID 2 should be equal to A. If it is false, then only user ID 2 should be equal to A. The last set of entities that I'm going to talk about is post, comment and like. Let's go ahead and create entities for all of them. So there will be a post entity. Inside this post entity, we'll have an ID. Now, what is the relationship of a post with a user? One user can have multiple posts, whereas the reverse is not true. One post will be written by just one user. So let's add user ID in the post entity table. Whenever you have one to many kind of a relationship or many to one kind of a relationship, add that attribute of the first entity in the dependent entity. So the first entity over here was user, so we'll have user ID inside post ID, which is the dependent one, and some text to go along with it. Similarly, in comment entity also, we'll have an ID. Comment is made by a user, so comment is dependent on user ID. Comment is also dependent on post because a comment cannot exist independently of a post. So we'll also have a post ID here. Again, this is an example of a many to one kind of a relationship, and it will also have text. Now for likes, we can have 2 tables. One is a post like table. Inside post like, we'll have ID, post ID, again one to many kind of a relationship, and a user ID. On a comment like table, we'll have the same attributes, ID, comment ID and user ID. If you notice here, the post ID and comment ID are basically the entity IDs that this like is made on. So for example, in post like, the entity was post. In comment like, the entity was comment. We can club these 2 tables together, similar to we saw in educational and company. Combined table will look something like a like. Like will have an ID, it will have entity ID and entity type. Now this entity type can be of 2 types presently, either post or comment. Finally, we'll also have the user who has liked this particular thing. If I want to add one more entity, let's say a user can have vlogs as well. So what I'll do is I'll create a vlog table over here, and in this type, I'll add type equal to vlog as well. So without even adding one more table, my like table will work. I hope this video gave you some sense of how to design schema for big systems like LinkedIn. This is just a glimpse of what we teach and how we teach at Scalar. Lastly, we'll keep on adding videos on similar topics. Therefore, please subscribe to our channel to get notifications about new videos. Hi, I'm Mohit Yadav and I teach at Scalar. In this video, we are going to talk about Delicious, which was a site that started off as a college project and then scaled to 5 million users. In this video, we are going to learn about vertical scaling, horizontal scaling, and the challenges that comes with it. Now coming to the topic, Delicious. Delicious was a website that offered users to save bookmarks so that they can access it from any computer. The website was started in 2003 by a college student and was later acquired by Yahoo in 2005. This was way back when Chrome was not there and there was no bookmarking service either. By the end of 2008, the website had more than 5 million users and approx 180 million bookmarks saved. This scaled from one laptop to 5 million users. We'll start from the day it went live on the creator's laptop. Let's start by understanding what happens when you type delicious in the browser. Now, browsers do not understand the names. They only understand IP addresses. Hence, we need a way to convert this URL into an IP address. In case of delicious, DNS will return the IP address of the computer on which it is hosted. Now, since every machine which is connected to internet gets an IP address, and every time we connect to internet, this IP address may change. Therefore, we need to associate a static IP which does not change when you connect to internet again and again. And we need to assign this IP to the computer. To get the whole system up and running, we first need to purchase a domain name called delicious and then map it to the static IP of this computer. If you look closely, there are two major kinds of requests involved. One is the get or the read request in form of get user bookmarks, and the second one is post or write request in form of add bookmarks. Using the IP address that is returned from the DNS, both this request will go to the same computer. And within the computer, there will be two things running. One is the application server, which will listen to all the requests that are coming to the HTTP port 80. And the second one will be the MySQL server, which will store all the bookmarks that my users are trying to save. So till now, my life is good. I'm running the website for free and I'm using campus internet. My database is set up on my personal computer, so I'm not paying anything for the resources. And I'm making money out of ads. Soon, the website became an instant hit. The user base kept on growing and the challenges also kept on piling up in the same proportion. Every time a new bookmark was created meant that there is a need for extra storage to store this particular bookmark. Now, the best available hardware at that time was around 50 GB of hard disk, 128 MB of RAM. This was basically a Pentium 4 era. To keep up with the demand, he bought better hardware, meaning he bought a better laptop, a better computer. The bottom line is he bought more RAM or more hard disk or maybe multiple cores. But soon, even the best hardware available was not enough to keep up with the growing demand of the business. In fact, most companies of the era focused on upgrading their hardware to solve the growing needs of the business. This form of scaling is basically called as vertical scaling. However, Delicious founder was different. He knew in the longer run his approach will not work. Not only he will be restrained by his system resources, but he might also lose valuable customer data if his laptop crashes. This website is not reachable when his computer is turned off. Hence, this computer was a single point of failure. To overcome the challenges of vertical scaling, his friends suggested him to utilize their own laptops or computers. The idea was to uniformly distribute the incoming requests to available computers. This mode, where we are overcoming the scalability hurdles using multiple servers and computers, is basically called as horizontal scaling. Now, we know that the client talks to the DNS to get IP address corresponding to a particular website. But the question is, the website is now running on multiple server instances. We have, let's say, 4 servers running the Delicious website. Which of the 4 servers available should be stored in the DNS? If I randomly choose any of the available server, all the requests will go to that particular server and that server will eventually die. To fix this, have one machine whose responsibility is to route the traffic to the available instances. This machine will lie between the DNS wall and the servers that I have. And the DNS configuration in the registry, I'll mention the IP address of this special machine and not of any of the instances that I have. Now the question comes, won't this special machine also die if all the requests pass through it? The reason why this special machine will be able to handle higher traffic is because it is only routing the traffic that it is getting to one of the available instances. It is not doing any compute or memory intensive task. And modern day machines can handle up to 1 million requests per second. So using this, we have solved for high number of queries per second on my system. But there is one more problem that still exists. That is single point of failure. Just like any other computer, what if my special server also dies? To solve this, we can have a standby routing server which will not serve or route any request. When my main server goes down, swap the main server with the standby server. But how do I swap? Should I change the IP address in the DNS registry? Doing this will take minutes. Can we do better? Yes, we can. Remember, we assigned a static IP to a special server. The key here is take the static IP and assign it to the passive one. Passive one meaning the standby server. The special server we just spoke about is called load balancer, and we will study more about it in the upcoming videos. Hello, hi and welcome everyone to my new video on system design. I am Mohit Yadav and I teach at Scalar. I've been fortunate enough to work on systems that saw over 10 million concurrent users, and I've also built data pipelines that can crunch around 1 TB of data per day. Having led teams at Nutanix and Hotstar which have built such massively scalable systems, I'm here today to share the same knowledge with you all. In this video, we are going to learn about a very important system design concept called load balancing. To understand how a load balancer works, we first need to look at how a typical request flows through my entire system. A request will start from a client application. This client can be a browser, a web app, or maybe a mobile app. This client will call DNS to resolve the domain name that I'm trying to access. For example, if I type delicious.com in the browser, the request will go to the DNS server. DNS server will give the IP address corresponding to delicious.com and it will return it back to the client. Subsequent request will then go to the IP address that is returned by the DNS. This IP address can either correspond to the application server which is capable of catering to that particular request, or it might correspond to a proxy server which will act as a gateway to route requests to the application servers. Since this DNS happens to be the first point of contact for almost every request on internet, this system needs to be very scalable and available. The amount of load that this system takes is immensely huge as compared to any other system in the world. Also, the latency, which is nothing but a measure of time it takes for a system to respond to a particular request, needs to be extremely low. What would be the total latency over here? If I have to calculate the total latency of the system, it would be DNS resolution plus the request time. So request time will be application dependent, but the time it takes for DNS resolution is same for every request on the internet. If this time is high, the overall latency of the system increases. So my goal as an engineer should be latency of the DNS resolution should be extremely low. And to achieve this, we try to cache the DNS mapping at various stages. What are the various stages? We try to cache it at the browser, we try to cache it at the OS, ISPs, and then we also replicate it to DNS servers. There's one more important thing. Now assume that if the DNS servers are placed at only one geographical location, let's say US, and the requests are originating from, let's say, India, it will add lot of latency because India and US are geographically apart from each other. And that's the reason this geographical distance will add to extra latency. Typically, it takes around 200 milliseconds for a request to reach from US to India. So every request which is originating from India and is getting resolved in US will have an inherent lag of 200 milliseconds. It is not a very desirable outcome, right? So to avoid that kind of scenarios, DNS is basically replicated across the globe. And because it is replicated across the globe, updating or changing the IP address on these DNS server is not a very easy task. This change will have to be propagated to the entire world, which might take hours or even days in some cases. I have a wonderful resource in the description that you should refer to understand how a typical DNS works. Also, I would like to pause here and request you guys to please like and share this video and support our free content on system design topics and software engineering in general. Now, coming back to the topic, in the example that we considered, the DNS was just returning one IP address. It will work for most of the websites in the world, but Consider this DNS resolution to be of Google or Facebook scale. Basically a tech giant which have massive amount of queries, massive amount of user base, and they process billions of queries per second. In those cases, if I just return one single IP address, chances are that all the requests of the client will hit that particular instance, and there is no such instance which would be able to handle traffic of the entire world. So that machine will eventually die. To avoid this, what typically these tech giants do is they deploy multiple IPs on which the client request will resolve to, right? So instead of returning, let's say IP1, they return a list of IP. So IP1, IP2, IP3, IP4, and they send this particular list to the client. Now it is the responsibility of the client to figure out which IP to talk to. Typically, in DNS resolution phase, it tries to follow up something called as a waterfall model. What is a waterfall model? It will try to connect with the first IP. If the connection is successful, it will not connect with IP2, IP3 or IP4. If the first connection itself is successful, it will connect with the first IP. Now, if all the clients will start connecting to the first available IP, that also is not solving the problem. Even though I'm returning a list, but essentially each client is connecting to the first IP that is returned. So if I return the same IP list to every client, I will be gated by a limitation that every client will try to connect to the same IP. What DNS do is, instead of returning the list like this, they return the list in a shuffled order, meaning that it is very much possible that user 1 gets a list like IP1, IP2, IP3 and so on. User 2 gets a slightly different order like IP2, IP1 and IP3. User 3 gets a list like IP3, IP2 and so on. This way, I have successfully distributed the load to my available instances, right? Another way to do traffic routing is to use a geo-based routing strategy. That means people who are residing in India will get an IP address corresponding to India data center. People who are residing in US will get an IP address corresponding to US data center. That also bridges the latency gap. Why? Because if user sitting in India gets a IP address of the data center in US, there will be an inherent lag in resolving the subsequent request. So it makes sense to have a geo-based routing strategy as well. Now we have identified the IP address which will be responsible for answering all my client requests. This could either correspond to a single server or a gateway server which will route traffic to my available servers. If we choose to route the entire traffic to a single computational server, the only way to scale is to run our application on a better hardware. However, if we choose to route traffic via gateway server, we can add more instances as and when required, and adding more instances will help us cater to multiple or higher number of incoming requests. Another important advantage of this approach is that this allows application servers to keep evolving without the need to make DNS changes. Now this DNS changes, we have learned that it might take hours or even days in some cases. So if we have to update the code of my application server, all I need to do is add more application server, let's say AS1, AS2 and AS3. Register these application server in the load balancer and deregister the older ones. And I have saved myself from updating the DNS record. If this was the one server case, the IP address of that one server would have changed and I would have to update the DNS mapping as well. Lastly, one very important benefit that we are getting out of having a gateway machine fronting my application server is that this gateway machine also provides a layer of security. How? All the machines that are below the load balancer can typically be in my private network. meaning these instances can typically be disconnected from internet, and whenever they want to be using any data from the internet, it will come only via load balancer. So my load balancer is the wall that connects to the internet, and my application servers just talks to the load balancer. The load balancer also takes care of encrypting and decrypting the message and securing the request via HTTPS. So my load balancer layer can typically be HTTPS, and my application server can implement a HTTP protocol. Now there are two major types of load balancer. One is a hardware load balancer and the second one is a software load balancer. A hardware load balancer is a specialized hardware which takes care of routing the requests that are coming to it. Most likely you end up using a software load balancer which can run on a commodity hardware to route traffic. And this software load balancer is again divided into two types. One is a layer 4 load balancer and the second one is a layer 7 load balancer. This layer 4 and layer 7 translates to the OSI network layer, right? Layer 4, if you remember, is a transport layer, and layer 7 is basically the application layer. In the transport layer, the only thing that we get from the incoming request is the IP information. So we only get the source IP, and based on the source IP and the port in the incoming request, we route the traffic to the available servers. Whereas in the application load balancer, we get much more richer information in form of the headers that are passed in the request, the query params, the path params, and also the HTTP method. But what are the pros and cons of using both, right? In what cases should you use layer 4? If you look closely, in the transport, we only have to rely on source IP and port. And based on this, we route the traffic. So the amount of computation that we are doing in the layer 4 load balancer is less as compared to the computation that we are doing in application where we are processing the entire request. So in layer 4, it will be much faster to route the request, whereas in layer 7, it will wait for all network packets to arrive before deciding which server should be able to serve my incoming request. But these days, we are having much better hardware, which are drastically reducing the slowness factor of layer 7. However, there is one more distinction why you should still use layer 4 in some cases, because in layer 4 we are exposing only minimal information to the load balancer. We are only exposing the source IP address and nothing else. Hence, layer 4 load balancers are slightly more secure as compared to layer 7, where we could extract the entire information about an incoming request. The last thing that we want to look at is how do we even route traffic from a load balancer to my available application server. Load balancers keep a registry of all the available application server. So it will keep AS1, AS2 and AS3, and it will also maintain the state in which these systems are. So for example, AS1, 2 and 3 are in available state, so it will mark it with green, and if there are other servers which are not in available state, it will mark it with red, and request will not be routed to those servers. But what should be the routing strategy? Our goal is to try and optimize on the resources that we have, and based on the resources, we should route the request. One of the very trivial or the brute force way to route traffic is to send the first request to first server, second to second, and the third request goes to the third server. The fourth request again goes to the first server, fifth request goes to the second server, and sixth request goes to the third server. And we'll keep on doing this circular distribution of requests to all the available servers in my system. This kind of routing strategy is called as a round robin strategy. But as you can see, this is not a best strategy to go for. Why this is not a best strategy? We can see that the application server 2 has twice the RAM, twice the number of cores, and twice the number of disk available as compared to application server 1 and 2. Therefore, it should ideally process more number of requests as compared to the other servers. So what we can typically do is make the routing strategy in such a way that application server 2 gets approximately twice the number of requests as compared to my other available servers. How I can do that? I'll route first request to the first application server, Second request will go to my second application server. Third request will also go to the same server. Fourth goes to application server 3. Fifth goes to 1. 6 and 7 goes to application server 2, and 8 goes to application server 3. That ways, first server gets 2 requests, this gets 4, and the last server will get again 2 requests. Application server 2 is getting 50% load, application server 1 is getting 25% load, and similarly application server 3 is also getting 25% of the load. This kind of routing strategy is called weighted round robin. The other routing strategies worth mentioning over here is a least connection routing strategy. This least connection looks at the number of active connections that are there with the application server, and server with least number of active connection will get the next new incoming request. For example, if there are 5 connections to application server 1, 6 connections to application server 2, and let's say 4 connections to application server 3, the next incoming request will go to application server 3 and this number will increase to 5. As soon as this request is processed, the number will again decrement to 4. Here also we have the same problem as in round robin strategy, that we are not accounting for the capacity of the instance. To accommodate that, here also we have a weighted least connection routing strategy where you can assign weights to a particular application server and routing will be done based on that. The last strategy that I'm going to talk about is basically a least response time strategy. In least response time strategy, we look at 2 parameters. One is the number of connection it has, and the second is the average time it takes to complete a particular request. Considering these 2 parameters, we decide which server should cater to my next incoming request. Now, all these strategies that we have covered till now work well if every app server is equally well equipped to answer my query. Meaning that if I have a query A, I will get the same response if I send the query A to application server 1, to application server 2 or application server 3. Regardless of where this query is getting processed, I will get the same response. This kind of a system is basically called as a stateless system. The last set of routing strategy that I have not covered in this video is called a hash-based routing strategy. In this hash-based routing strategy, we use the source IP address or the URL and we calculate a hash out of it. We have another video on consistent hashing to explain this routing strategy in depth. So please go ahead and watch the video on consistent hashing to know more about the hash-based routing strategy, right? This typically works on stateful systems. Again, stateful system and stateless systems is something that we are going to cover in the upcoming videos. So please stay tuned for that video as well. Hello, hi, and welcome everyone to my new video on system design. If you are a software engineer, chances are you would have heard about terms like stateless and stateful systems. This video is a beginner's guide to understanding these terms and have practical insights about when and where to use these systems. I'm Mohit Yadav and I teach at Scalar Academy. I've been very fortunate enough to work on systems that saw over 10 million concurrent users and have built data pipelines that can process terabytes of data per day. Now let's get started. Let's say you're building online calculator and you're asked to add 2 numbers. Do you appreciate that every server in the system is equally well equipped to answer this query? It doesn't really matter which user is asked to do these operations. Every server in the system will yield the exact same result. The reason each server is able to do so is because the servers are not saving any context or state. This makes every server equally favorable to answer that query. Such systems are called stateless systems because they're not storing any state, context or any data in the application server. Now let's consider another example. Let's say we are trying to build a chatbot this time and one user sends a query asking for restaurants that are nearby his location. The chatbot first saves this message in the memory and then responds with a list of restaurants nearby. It then asks the same user to pick one restaurant out of the list. Now the user, let's say, choose third restaurant And if this request goes to the same application server, it will be able to return relevant information since it has context about the previous chat history. However, if this request goes to some other server, that server will not be able to comprehend the message properly due to the absence of previous conversation history. Therefore, in such systems, the context of the conversation really matters. This context can be decoupled from the application server by simply adding a storage layer to save the messages. Such systems where the context or the state lies within the application server are called stateful systems. Now that we understand what are stateless and stateful systems, let's take a moment to appreciate the pros and cons of each system. We'll start off with stateless systems, which are very easier to scale. The reason is that each server in the stateless system is equally well equipped to handle the request. Thereby, if the load on my system increases, I can just add or remove servers in the system and my entire infrastructure will work just fine. These systems are also resilient to server failures because there is no state which is maintained at the server, and even if one server goes down, there is no actual loss of data, and the lost server, we can just replace it with a new one and my system as a whole will work as expected. However, most of the systems that you will design will need to store some state in some way or the another. If you want to keep the system stateless, chances are that you will store this data or this state in a storage layer. Now, querying this data will involve a network I/O call. This operation will drastically slow down your system performance because you are involving a network I/O call. Reading the data from your application server will be slower as compared to doing a network call and fetching the data from the storage layer. Now let's compare this with the stateful systems. Since the context or the state of data required to answer client queries reside within the application, the latency of stateful system is much lower as compared to the stateless ones. However, these systems are not resilient to server failures. If one of the system goes down, the data that was residing in the application goes down with it. Hence, it makes sense to store either the derived data or the data which is actually very short-lived. Because of this, it is also harder to scale, right? It is quite difficult to scale such systems because with the increasing number of requests, we will have to transfer some amount of state from one server to newly added server. This might sound trivial, but in reality, it poses many risks associated with distributed systems. You would have heard somewhere that stateless systems are beautiful and software engineers should always try to design their systems to be stateless. This is true in most of the cases, right? Because we can just add or remove machines and the load of the entire system will be uniformly distributed. However, in some cases, it is essential to store the data locally in the application server as well, especially in cases where the state is very short-lived. I'll give you one very good example. Let's say you're designing a multiplayer game like PUBG. If you store the state of a particular match in a separate storage layer, the latency of the entire system would be huge. Imagine somebody shooting someone in the game. That state is stored in a separate DB and it is propagated to multiple users who are also playing the same game and they are reading from the DB. There will be a lot of lag. Hence, the latency of such systems needs to be very low. So what we do is we store the state of such applications in the application server itself. Also, it is important to note that the state of a PUBG match is very transitive. We will not need this information once the match has ended. Hence, in such cases, stateful systems makes more sense. In nutshell, just like any other system design concept, deciding which system to go for depends upon the use case in hand.
Ever wondered how games like PUBG scales horizontally? We learned that designing a game like PUBG would require us to save the state in the application server itself. We also saw that this state is very short-lived. To understand why, let us see what information we are storing about the game. Every game will have players and each player will have to store their location on the map, their health, weapons and the team information that they are playing in. We need to store this information only till the match is live. Once the match has ended, we can destroy this particular information because it does not make sense. If we store this information in a database, we'll end up wasting a lot of time. Why? Because we'll have to query the database every time a person requests for the match state. And this is an IO call, network IO call, which will waste a lot of time. Hence, it is critical to store this information in the application server itself. Now, in order for a match to work seamlessly, all players of a particular match must be routed to the same application server. Else, they won't be able to find the relevant data for that particular match. To achieve this, what we can do is, we can assign a match ID and ask our client to send this match ID whenever they are making a request. They can send it as a path param, they can send it as a header, they can also send it as a query param. The thing to note here is that the load balancer must ensure routing the traffic based on this match ID. In simple words, if the first request for, let's say, match ID 2 goes to server 1, all the subsequent requests of same match ID must be routed to server 1 only. Which algorithm can we use to distribute this traffic? Well, in this video, we are going to discuss one such approach. We are also going to look at its pitfall and build intuition for the upcoming video on consistent hashing. I am Mohit Yadav and I teach in Scalar Academy. I have been fortunate enough to work on scale at Hotstar and Nutanix, where I build systems which has massive read and write volumes. One of the reasons behind doing this system design primer series is to impart the knowledge that I have gained over the past 1 decade and help budding software engineers get better at architecting systems. Now, coming back to the topic. Remember, our goal was to distribute the load in such a way that all the requests with same match ID must be routed to the same server. Match ID 2, server 1, all subsequent requests of match ID 2 going to server 1. The second point was that the load should be uniformly distributed. Meaning, if I have n servers, load on each server must be equal to or must be nearly equal to 1 by n. And finally, I should be able to add or remove instances from the cluster. Why? Because that is the essence of horizontal scaling. I don't want to build an infra where I have constant number of machines. My load on the system can increase or decrease. Depending upon that, the number of servers in my cluster can increase or decrease. The first strategy, if I have to think about the approach, the first strategy that comes to my mind is that I have a match ID, and if I have to route traffic to each of the servers evenly, the basic strategy that comes to my mind is that I can simply take a mod of match ID with the number of servers, which is n. This number will signify which server will process my request. Let's take a few match IDs to see how exactly this is going to happen if we have 3 servers running. Let's say the match ID is 11, 11 mod 3 is 2, 42 mod 3 is 0, so it will be routed to the 0th server. 34 mod 3 is 1, so it will be routed to first server. Similarly, 53 mod 3 is 1, 63 mod 3 is 0, which will be routed to 1 and 0th server respectively. We see that the above approach will satisfy my first 2 goals. Let's dig a little deeper to find out what will happen if we add 1 more server. Now my number of servers or n becomes 4. So let's consider all the examples, all the match IDs that I took in the previous case where n was equal to 3. So now since n is equal to 4, 11 mod 4 will become 3, 42 mod 4 will become 2, 34 mod 4 will again be 2, 53 mod 4 is 1 and 63 mod 4 is 3. Now let's consider the other case where we are removing one instance from the cluster. 11 mod 2, 1, 42 mod 2, 0, 34 mod 2, again 0, and 53 mod 2 is 1, 63 mod 2 is again 1. Now what is happening here? Let's consider the first case. If the match ID is equal to 11, which was getting routed to server 2 when we had 3 servers, will now be routed to server 3 when we add a new instance. unless we transfer the data which is already residing in server 2 to server 3, our users will not be able to get the match information. And as we can clearly see from the examples that we took above, whenever there is a change in the number of servers, a majority portion of the keys will be distributed to the new servers. And this by no means is an ideal behavior. We need a way to minimize the need of data transfer whenever we decide to add or remove instances. Now, before winding up, I would like to give you a home assignment. That's a maths puzzle. The puzzle goes like this. Consider initially there are m servers in the cluster and you can add or remove servers from the clusters. Let's say you do some add or remove operation and the final number now becomes n. This n can be greater than m, meaning that I have added new servers in the cluster, or it can be less than m, which means that I have removed few servers from my cluster. What you have to do is you have to write an equation using which you can find out the amount of data that will be moved. Write your answers in the comment section and we will see who gets it right. I hope you all get an idea about basic approach for load balancing in stateful systems. We will look at a better approach which is consistent hashing in the upcoming video.
How do you distribute the load evenly in stateful systems? In the last video, we saw one such approach where we used the modulo hashing. The approach works perfectly fine until we decide to add or remove the instances. Whenever we want to add the instances, a majority portion of the keys needs to be rehashed. In this video, we are going to look at a better approach called consistent hashing. I am Mohit Yadav and I teach in Scalar Academy. Now coming back to the topic, let's have a look at the problem statement again. Our problem statement is that we need a distribution scheme that does not directly depend on the number of servers, so that whenever we want to add or remove servers, the number of keys that needs to be relocated is minimized. To understand the solution, let's visualize a circle with marking 0 to a very large number, let's say 10 to the power 18. And we'll call this particular ring or a circle as a consistent hashing ring. Then we'll take two hash functions which will basically generate keys in the range of 0 to 10 to the power 18. Let's call them HS and HC. The HS hash function will be used to mark servers on the consistent hashing ring. The HC hash function can be used to mark partition key or the client ID on the same consistent hashing ring. Now to find out on which server a given key needs to be routed, we need to locate the key on the circle and then move in the counterclockwise direction to find the server. Now there are two main problems with this approach. First, uneven distribution. The server which is located at the max distance in the counterclockwise direction will get the most number of requests. And the second one is the weighted routing, wherein we might have a scenario where one server has twice the number of resources as the other servers. In that case, we need to ensure that the servers with more resources gets more number of requests. To solve for the other problems, what can we do? We can assign many labels to each server. So now instead of having labels A, B, C for three servers that we had, we'll have server labels between A0 to A9, B0 to B9, C0 to C9, all marked in the same circle. Now if server B is twice as powerful as the rest, it could be assigned twice as many labels. As a result, it would end up holding twice as many objects on an average basis. This way we can be sure that the keys are evenly distributed and server with better resources are holding more amount of data. Now let's see what happens when we remove one server. Imagine that server C is now removed. To account for this, we must remove all the labels between C0 to C9 from the circle that we had, the circle which was basically representing the consistent hashing ring. This results in the object keys reassigned to server A and B. Whatever keys were residing in server C
will now be reassigned to server B and C respectively. But what happens with the other object keys? The ones that originally belong to A and B? The answer is nothing. Absolutely nothing. And that's the beauty of consistent hashing. The absence of CX label does not affect the keys in any way. So removing a server results in the object keys being randomly assigned to the rest of the server, leaving all the other keys untouched. And if you notice closely, all servers are still holding 1 by n amount of data. Earlier also they were holding 1 by n. When they had 3 servers, they were holding 1/3 of the data, and then when we removed one server, every server is holding 50% of the data. Now consistent hashing is used to uniformly distribute the data in stateless systems like Kafka, Cassandra, etc. It's also a very powerful tool that finds its application in the stateful servers, as well as it is a way of implementing sticky sessions in the load balancer. I hope you got an idea about what consistent hashing is, how it works.
Hi, my name is Anshuman and I'm one of the co-founders at Scalar Academy. If you are new to tech and you have recently heard the term caching and don't know what it means, then this video is for you. I was fortunate to see scale at Facebook. I was fortunate to be part of teams that build products that scale to millions of queries per second and billions of users. I'm here to share some of those learnings with you.
All right, so I'll try to explain caching as simple examples as possible. By the way, there is a bonus problem at the end of this video, so please do stay till the end of the video to look at the solution of that. All right, so let's imagine that you want to make milk tea. One obvious ingredient of milk tea is milk itself. And milk I find in most grocery stores, department stores that are around me. So one obvious way whenever I'm making milk tea is that I go to the department store, fetch milk from here, and then make my milk tea. This to and fro process, by the way, ends up taking a lot of time. However, one thing which strikes me is, by the way, I can buy a refrigerator. I can buy a fridge which stays in my house only, where I can buy few milk cartons at a time and I can store it here. And when I'm making a milk tea now, then as long as there is some milk present in the fridge, I can use it from here. If there is no milk present in the fridge, then I go to the department store and I buy the next set of cartons of milk. So what have I done in the process? I could still have gotten milk from department store. It's the same milk. However, I created this temporary storage which is close to me, which is much faster for me to be able to store those milk so that I can make my milk tea faster. Plus then I have more motivation to make milk tea because I have it in my fridge. Very similarly, if you look at the design world, distributed systems world, you always have these systems that are looking for some or the other information, right? So machines talk to each other, they query for information. Imagine you load your Facebook profile page. That profile page would need to show your name, email ID, your friends, etc., etc. So for that, it would need a lot of information. So this machine would then ask for profile information for yours, which would be there in some other machine in the hard disk. And reading from hard disk is slow. If you would have noticed, when you transfer movies, etc., from your friend's laptop, those movies are written to your hard disk, and those hard disk writes are fairly slow. Very similarly, reading from the hard disk is also slow, especially if your data is lying somewhere you don't know where. So you'll have to search through the index to find where this profile information is and then fetch that data from there. However, if the same information was in RAM somehow, which is main memory, then accessing that would be faster. However, I mean, if we're talking about Facebook has so many people, so many profiles, all information cannot reside in RAM. It has to be in the hard disk, which is the same as me going to the department store every single time when I want to make milk tea. However, if I know that there are, let's say, certain profile pages that are fetched very often, that are more likely to be fetched than the other profile pages, then maybe I can create a fridge, a refrigerator, where I can store the information of these pages. So that when somebody asks for these pages, then I don't go to the departmental store, which is the hard disk in this case. Maybe I have that information in RAM or a faster memory access. I mean, let's not say RAM, some place where I can find that information faster than actually having to read from the hard disk of a different machine. That process is called caching. Caching is exactly what I did with my refrigerator to department store. It is exactly doing that to reduce the latency of fetching that information in some cases. A cache will never be as big as your total storage. There will always be cases when I run out of milk in my refrigerator or when the information is not present in this fast storage. And that process, by the way, this is caching. And when I find data in my cache, it's called a hit. When I do not find the data because it is not present, therefore I'll have to go to the departmental store or go and read from this hard disk. That is called miss. So whenever you find data in the cache, it's a hit. You don't find it, it's a miss. That is caching. And caching is something, by the way, you encounter on a day-to-day basis. For example, you might have noticed that when you load a website for the first time, it's usually slower. But when you refresh, it loads faster. Sometimes when your internet is not working, you keep refreshing after a while, and eventually the website loads. Your internet doesn't get faster. That's not the reason why it loads. It loads because once, let's say there was an image on the website. Once that image has loaded, that means your browser has now gotten that carton of milk. So it caches that in its own memory. On your browser, on Chrome, it gets cached. So next time when you load the same website with the same image, the browser doesn't go and fetch the entire image from the other website. It only checks if it was the same image. If it was the same image, then it fetches it from its local memory, which means I don't have to go over that slow internet to fetch that image. And therefore, by using caching, I have significantly reduced the latency of fetching that data. That is caching with your browser. Systems within also do caching in various forms. One simple question I have. If you haven't seen my cap theorem video, please go and see that, because this question is slightly based off that. Imagine you are building a very consistent system. You would want that if you're doing caching, then this cache data is exactly consistent and exactly the same as the data present in your hard disk for whatever entries it has. If you're building a consistent system and you're doing caching there when I ask you to update, how do you go about updating such a system? In the context of the departmental store and milk tea example, let's say that you want your milk tea to always use the latest milk that is present in the department store, or always use the milk that is present in the department store. How do you validate that the milk that you have in fridge as of now is exactly the same milk that is present in department store? How do you do that? There is something called as, well, actually, if you look at how you would do it, there are only two ways of doing it, right? One is when you tell me that, hey, here is new milk to restock your store with, or here is new data, right? Which is, let's say, and on my profile name, for some reason, my name changes. So whenever there is data pertaining to me that is being updated, it does not go directly to the hard disk. Imagine this is my hard disk or hard disk storage, and here is cache. Whenever this update operation comes, it goes through the cache. So first I check, is this entry present in the cache, which is my name, is my profile cached? If it is cached, then I first update the entry in the cache, and then I update the entry in the hard disk. And only then, when both of them have been updated, only then I return success. This is called write-through cache, which means whenever new milk comes to the department store, it goes through me. It goes through my house. I do a verification and only then I let the milk pass. That is write-through cache. Or the other way could be that if the database is aware of where my caching system is, whenever there is a profile update, the database tells cache to throw away whatever information I have regarding my profile, because that is now out of date. And only once invalidation has been done, only this write has been done, invalidation has been done, only then you return success. Or in the context of, again, departmental stores as well as milk, let's say whenever my department stores gets a new kind of milk, they call me up and they say, hey, look, please throw away the milk that you have in your refrigerator. It is old now. We have a newer quality of milk. And that way I make sure I'm always cooking my milk tea with the newest quality of milk that I have in the market. That way I stay consistent. That was all for me for today. I hope, again, caching made sense to you. You understood why caching happens in systems.
Hi, my name is Anshuman and I'm one of the co-founders at Scalar Academy. If you're a techie, chances are you would have heard about CAP theorem. Today we would talk about what C, A and P in CAP theorem stand for, why it works the way it does, and what does CAP theorem mean in the modern ecosystem. I was fortunate to see tech at scale at Facebook and was able to design products that served millions of queries per second and billions of users. I'm here to share a few of those learnings with you.
All right, so let's first look at why do we even need to learn CAP theorem. CAP theorem is one of the most basic principles of distributed storage. So if at all you think about building or working on distributed systems in the future, CAP theorem is a must-have, must-know. So that's why you need to learn CAP theorem. Now, before I get into explaining CAP theorem, and I would try to do that with using as simple example as possible, I want to give credit to Kaushik, whose blog I have borrowed a few ideas from. So thank you, Kaushik, for coming up with a very, very innovative example. So let's get to it, right? So to elaborate CAP theorem, I'll take example of a real world example of let's say you. Imagine I am an entrepreneur. I'm looking for ideas and I feel, you know what, like people need reminders. Let's build a service that just stores reminders, right? Which is, I get this very premium number. Imagine I name my company as ABCD. And I get this very premium number, which is 1234, 1234. People could just call me on 1234, 1234, and they can tell me what they want to remember. And then when they call me back, I tell them what they wanted to remember, and then things work. It seems to me that this is a great idea. So what I do is I set up this line. I sit in the office. Imagine this is me. Forgive my drawing. Imagine I sit in the office. Every time somebody tells me, let's say I got a call from X, and X says, hey, please remember that I have a flight tomorrow at 9 p.m. I say, great. Next time they call and they ask me, tell me what I wanted you to remember. And then I tell them, you know what, do you have a flight tomorrow at 9 p.m.? And then this seems great. I charge people very nominal amount of money to store this information, and service takes off. Everybody needs this. There's a big market. Everybody starts using it. And then I start to hit the problem. And you'll notice most systems, they start to hit the problem when they hit scale. Then I realize that I'm getting a lot of calls and I'm not enough to address all of those calls myself. So then I start to think, and then I think, sure, let me get my wife also involved. So now this number actually has me and my wife. Both of us sit with our diaries where the call gets routed to either one of us, whoever is free. And when I get a call, I just very quickly, if the person is asking me to take a reminder, I just take down that reminder, right? And when the person calls me back, I respond back with the reminder. Great. I have suddenly now doubled my capacity. If I was able to take 1,000 requests in a day before, now I can take 2,000 requests because I have my wife to help me as well. Very soon, I got my first unhappy customer. Mr. X calls me one day and says, hey, can you please remind me when is my flight? And I look through my diary and I realize I don't have an entry corresponding to Mr. X. And I tell Mr. X, hey, look, I don't have an entry corresponding to you. Mr. X seems very disappointed, very angry, and then disconnects the call. Now I start to think, what might have happened? Either Mr. X was delusional, or maybe there was a fault at my end. And then I see that there might have been a problem. It is possible when Mr. X wanted to store their reminder, they might have called my wife. And my wife would have stored this entry that, hey, X wants a reminder for a flight at 7 p.m. tomorrow. However, that entry is not with me because that call never came to me. However, when X wanted to understand when their flight was, they ended up calling me instead of my wife because they don't know. They only know this number, 1234, 1234. And I don't have that entry. And this is why X is very unhappy. This is what is called as consistency problem, data consistency problem, which is an end consumer might have stored some data with me, and when they ask me back, there is no guarantee that they will get the data back because it depends on where the request comes to. If the request comes to my wife, they'll get their data back. If the request comes to me, they'll not get the data back if my wife's diary has that entry. This is a big problem. If not solved, my company will die. So I start to think, and I come up with a solution. I say, hey, look, here is what we could do. When X calls me to say that, please note down that I have a flight tomorrow at, imagine 6 p.m. I'll note it down in my diary. I'll also tell my wife to note down this entry, which is also that tomorrow 6 p.m. flight. And only when both of us have written the entry in my diary, in their own diaries, then I return success. Then I tell Mr. X, I have noted down your entry. That way, there is guarantee that both of our diaries, my diary and my wife's diary, they'll have the exact same entries. Consistency of data. They'll have the exact same entries. And great, my consistency problem is solved. Now, when X calls any one of us, we can respond back with the right data points. Things were going great. One day, I again start to face a problem. One day, my wife calls in sick. She's not keeping well, so she's not in the office. What that means is that my wife, for the time being, is gone. For a day is gone. And at that very moment, another gentleman, Y, calls me and tells me to note down an entry. I say, okay, sure, what's your entry? And they tell me, you know what, I have a flight tomorrow at 3 p.m. I say, great, let me note it down. Let me, by the way, also go and tell my wife to note it down. Oh, by the way, my wife is not here. She can't note it down. And therefore, I'll have to tell Y that, hey, I can't note down your request. Your request actually has failed, which means for the entire day, I can't take in any new requests. That is a availability problem, which is my system is not available to take all kind of write requests. In the case of software systems, for example, like Facebook, you could think of Facebook saying that for an entire day or for an hour or for a few minutes, you can't make any new posts or you can't post any new photos on Facebook. That is an availability problem. So again, I'm very stressed. What do? I don't want my business to fail. So I think and I come up with another solution. I say, you know what? When my wife is not here, so I have my diary. And imagine my wife is not here. So I have written a bunch of entries. This new day comes. Whatever entries I get, Mr. X says to note down something, I'll note it down. When Mr. Y says to note down something, I'll note it down. And when my wife returns back, because I want both of our diaries to be identical, I tell her, look, you'll not take up any phone calls till you have noted down all of the additional entries that I made in the previous day. Or if she was gone for last 2 days, then in the previous 2 days. So you first note down all of the additional entries and then you start taking calls. And then my problem is solved. Now, because if X calls me and says that, please note down that I have a flight tomorrow at 8 p.m. Even if my wife is not in the office, I can still note down the entry. And therefore, I'm still available. Since my wife will come back and she will actually catch up with whatever new entries are there in my diaries before answering any phone call. So we're also consistent, which is great. Things are going super good. And then comes another problem. One day, me and my wife, we both have fight and we stop talking to each other. So imagine I get a phone call, X says, hey, look, please note down, I have a flight tomorrow at 9 p.m. I can't note it down because I'm not able to talk to my wife. And if I note it down, then and tell X that, hey, look, I have noted down your entry, then my system becomes inconsistent, right? Because my diary has now different entries, my wife has different entries, and she's still taking calls. So when this network partition happens, where I'm not able to talk to my wife or other systems, then I have to make a choice. Do I want to stay consistent or do I want to stay available? If I want to stay consistent, then if Mr. X calls me and says, please note down the entry, I will have to say, sorry, I can't. My system is down. It's not accepting any new write requests. If I want to stay available, then I can take down the entry, but then I become inconsistent. So if I choose consistency, then I become unavailable. If I choose availability, then I become inconsistent. And that is exactly the CAPS theorem. CAPS theorem says that if you have consistency, if you have availability, and if you have partition tolerance, then at a time you can only guarantee 2 out of these. You can't promise all 3 at the same time, which means when this network partition happens, I would have to choose between consistency and availability. I can't have both. That's the CAPS theorem. Now I have 2 bonuses to add here. Most systems that are available and partition tolerant, which is called AP, A for availability, P for partitioning, C for consistency, right? Most systems that are AP can still make sure that they become eventually consistent. What does that mean? That means eventually my and my wife's diary, they have same entries. How do I make sure of that? Whenever we start talking again, we can exchange notes. Or maybe just imagine that there's a clerk here that I've hired who just takes up all of the new entries in the last 1 hour, tells me what those entries were, so I take those down. Also, by the way, ask me what were the entries that I made in the last 1 hour, goes back to my wife and tells, here are the new entries that were made in the last 1 hour. So there might be periods in between that I was inconsistent, but eventually we become consistent. So that is eventually consistency. There is one more extension to CAP theorem that was done very recently, actually not very recently, about 10 years back, which is called as PACELC theorem. And what this theorem states is that, hey, look, when network partition happens, when my systems can't talk to each other, then sure, you have to choose between availability or consistency. You can't have both. However, there are going to be cases when my systems can talk to each other, which means there is no network partition, which is else. So else, I have to choose between latency or consistency. I can't have both. If you notice, when I made this decision that to stay consistent, I will make sure that on every single call, I will make sure my wife also notes down the entry and only then I return success. Then I'm actually waiting for my wife to note down that entry. My wife could be doing something else at that time. My wife could be answering some other call. And in that case, the entire request might end up taking a lot of time. So the latency could become high because I want consistency. However, if I was willing to let go of consistency, which is I wanted to say that, hey, look, I'll just note it down and maybe my wife could probably catch up later on, then latency could stay really low. So then you actually have a balance between latency and consistency when there is no network partition. So that's what PACELC theorem is, which is just an extension to the CAP theorem, because CAP theorem does not talk about latency. I hope that made sense to you and I hope that was helpful. This CAP theorem is one of the most basic and one of the most useful theorems you'll come across when designing distributed systems. I'll keep doing more videos like this. If you like this video, please like the current video and subscribe to the channel. Thank you. Thank you so much.